Hello everyone and welcome to this first video on the signed particle formulation of quantum mechanics. Today we are going to talk about quantum mechanics without wave functions. So this might sound a bit strange. How can we do quantum mechanics without using any kind of wave function? And what we are going to see here is that actually this is possible, but we have to use now a different concept, which is not the wave function anymore, but it's a concept of a signed particle. So this is what we are going to talk about in this video. So let's start from standard quantum mechanics. Let's explain a little bit what we have today, what is the standard approach in quantum mechanics, before we can jump on more sophisticated or more advanced formulations of quantum mechanics. So what is quantum mechanics, first of all? Quantum mechanics is the branch of physics that deals with very, very small objects such as atoms or molecules. And while this might sound very, very theoretical and very far from real life, this theory has had many, many practical implications in our modern life. For example, it has helped to obtain better chemistry, it has helped to obtain electronics, which we didn't have before the understanding of quantum mechanics, but it also provided a way to understand the world around us. So quantum mechanics is actually a very, very important theory of physics. The standard approach of quantum mechanics is rather simple to explain in mathematical terms. First of all, quantum systems are described in terms of a complex wave function, the one that you see here that I am showing with the mouse. And essentially this wave function is usually named as a Greek letter psi. So the psi usually function, the psi function usually will represent a wave function. In this particular case, the wave function is defined over the space of configuration. So that would mean that if we have, let's say, n particles, this psi function here, the wave function, is going to depend on the position of every particle in the system. We then can use the Born rule, which is a heuristic rule, which explains us what we can achieve from the wave function, what kind of information we can get out of the wave function. And what the Born rule tells us is that the square of the amplitude of the wave function, which is a complex function, correspond to a probability. So if we take the square of the amplitude of the function psi, practically we are going to obtain what is the probability of finding a particle in a certain area of space. Moreover, the Born rule is of course not the only thing that we can use to make predictions or to understand the system. We also have ways to represent observables, and in standard quantum mechanics, observables are represented by operators. So this is a drastic departure from classical physics for sure, but it does work, and that's the standard way we do predictions in quantum mechanics nowadays. We have two equations to make predictions, or let's say we have two main equations which help us to predict what is going to be the wave function of the system. And essentially we have two main equations. The first one that I am showing here with the pointer of the mouse, which is the time-dependent Schrödinger equation, and the second one, which I am showing here on the bottom right of the slide, which is the time-independent Schrödinger equation. These two equations practically give us a way to compute what is the wave function of a system, but they do it in different ways. In the first equation, we are capable of understanding, for example, we are capable of predicting transitionary states or transitionary regimes, while with the second one, we are capable of predicting what are going to be the stationary regimes of the system. Other available formalisms exist, although they don't talk a lot about them in the literature, but they do exist, and they do have a meaning for their existence. In practice, all these formalisms explain exactly the same systems but with different mathematical concepts. So using one formalism will explain you part of the story or part of the system. If you really want to have an intuition on the system at hand, you will have to deal with different formalisms, and all of them have pros and cons and are adapted to a particular kind of, let's say, investigation that you want to perform on the system. Some of them are reported in these slides. For example, the very first one was the Heisenberg formulation, which actually came 1 year before the Schrödinger formulation, and which is based on the concept of density matrix. We then have the very famous Schrödinger formalism, which is based on the concept of wave functions, which was published in 1926, i.e. 1 year after Heisenberg. But then we started to see other formalisms arriving. For example, in 1932, the very interesting formulation of Wigner, which is based on the concept of quasi-distribution functions, but also the one coming from Feynman or from Keldysh, which are based on the use of path integrals and non-equilibrium green functions respectively. And in 2015, another formulation of quantum mechanics was published, which is nowadays known as the sign-particle formulation, and this is going to be the main topic of this video. So the sign-particle formulation was published in 2015. I am reporting this slide here so that you have a reference and you can download the paper, for example, if you are interested. So what is this sign-particle formulation of quantum mechanics? Well, it is based on the use of 3 postulates, and we are going to go through these postulates now. And we start from postulates 1 and 3 for the simple reason that these postulates are very simple to explain, and then we will go through postulate number 2, which require a little bit of more mathematical details. So postulate 1 says very simply that physical systems can be described by means of virtual Newtonian particles. In other words, they are provided with a position and a momentum simultaneously, and they also carry a sign which can be positive or negative. So the first postulate is actually telling you that it is possible to describe quantum systems by using a different concept, which is not the wave function. And this different concept is the concept of sign particles. So one could actually use an ensemble of sign particles to describe quantum systems. And we are going to see in more details what we mean by that. Postulate 3 instead tells us something different, and it tells us that if you have two particles with opposite sign and the same phase space coordinates, then they annihilate. So if you have, let's say, 2 particles, one with a positive sign and one with a negative sign, and they happen to occupy the same place in the phase space, or in other words, they have the same position and same momentum, then in that case they do not contribute to the description of the problem, or they do not contribute to the prediction of the behavior of the system. So they can be completely removed from the mathematical description, and we will see that there are advantages in doing that. So we can now go through postulate number 2. Which, as you can see, is slightly more sophisticated and requires some mathematical details. What postulate number 2 is telling us is that a sign particle that evolves in a potential V of x, in other words, a potential that depends on the position, the sign particles behave as a fieldless classical point particle, or in other words, it's going to create a pair of sign particles while behaving as a classical point particle in the same way it would happen in classical mechanics. Then the probability of creating this new pair of sign particles is going to be provided by this function that you see here, gamma of x, that is dependent on another function that is v of w, which is called the Wigner kernel, and which can be computed according to formula 2 that you see here. So in other words, if you have signed particles that are moving in space and these particles are in the presence of some potential v of x, essentially from the function v of x you can compute the Wigner kernel vw, and from the Wigner kernel you can compute the function gamma of x, which essentially tells you what is the probability of creating a couple of signed particles. And the last part of the postulate tells you essentially what sign this newly created pair of particles will have, what the position will be, and what the momentum will be. As a final note, I would like to make you observe that this integral here is not a Riemann integral. This integral was actually defined for the very purpose of computing the gamma function, and this is nowadays called the momentum integral. And the way this momentum integral is defined is according to this formula that you see here, formula 1, where this is essentially the limit of a sum. So gamma function, in a way, you can consider this as a sum, as a simple sum. So a few more things about the three postulates that we have just seen. First postulate, so postulate 1, it tells us something about the initial conditions. So what we have seen is that postulate number 1 is telling us that if you take an ensemble of signed particles, these are enough to explain the behavior of a quantum system. But what are the initial conditions of these signed particles? To explain this, I will start from wave functions, although this is definitely not the only way to do this, but this is definitely one familiar way to describe these initial conditions. So suppose that you have a wave function that corresponds to some initial conditions. So your wave function now depends on the position, but it's defined at time t equals 0. And we suppose that initial wave function is represented by this function phi of r, where r is the position. So now we can apply on this function phi, or on equivalently on the function psi at time t equals 0, we can apply what is called the Wigner-Weil transform, which is an invertible transformation. And out of these initial conditions, essentially, you are going to get, by applying this formula here, this integral, you are going to get now a quasi-distribution function. This quasi-distribution function can be easily discretized, and this is something that is actually very common in applied physics. It can be discretized, and all of a sudden, in this discretized phase space, you realize that you have this quasi-distribution function is essentially describing an ensemble of particles which can have a positive or a negative sign. The positive or negative sign is going to be given by the sign of the quasi-distribution function, and the number of particles that you are going to have in these cells of the discretized phase space is going to be proportional to the value of Fw, or to the absolute value actually of Fw, this quasi-distribution function. So once you have distributed your signed particles and you have given them a sign, then you end up having something like this picture here, where essentially you have a discretized phase space where your particles have been distributed, but they now also have a sign. And this is why we don't have colors here, but we do have colors here, where the color is essentially describing you the sign, but also the density of particles you have in that particular cell. So we can now go to postulate number 2, which is talking about the particle of the creation of particles. And in particular, we have seen that we have a probability that we can compute. So what this postulate is telling us eventually is that if you have, let's say, a particle that is starting where I am showing with the mouse, and this particle is moving as a fieldless particle in space and in time, eventually eventually it will have a high probability, that is coming from gamma function, it will have a high probability to create a new pair of signed particles. These signed particles, what the postulate is telling you is that these signed particles will have exactly the same position as the parent particle. One particle will have a positive sign and one particle will have a negative sign. And the way the momentum is computed for these newly created particles is provided by what is described at the end of postulate number 2. For postulate number 3, this is also very interesting because this provides computational advantages. So it is important that we describe a little, some details about postulate number 3. So what we have seen is that eventually out of postulate number 3, we can apply the process of annihilation. But we would like to see how this thing actually works. So you imagine that, for example, your particles, your signed particles, have been distributed now in your discretized phase space. If you let the system go according to postulates number 1 and number 2, even if you start from one particle, as you see here in the plot here, this is time, this axis here is time, and this axis here is the wave vector. And what you can see is the following. If you start with a positive signed particle, which is represented by this asterisk here in red, red represents positive, it will go ahead in time, but at some point it will start to create a new pair of particles. And as you can see here now, we will have two positive particles represented by these two red asterisks that you can see here, and it will also have one negatively signed particle, which is represented now by this blue round shape here. And if you continue, these particles now will create other particles, which in turn will create other particles, and so on and so on. So at the end of the simulation, you might end up having a lot of these signed particles, although we started in this numerical experiment from one single signed particle. So this means that essentially if we report the number of particles in time, what you see is that the number of particles can increase with time, even exponentially, depending on the system you have at hand. So this can be detrimental for the simulation because the more particles you have, the more objects you have to update. So this means that you have to perform more computational operations. So can we avoid this? The answer is yes, and the way we can avoid this is provided by postulate 3, which introduced the concept of annihilation. So in this particular case, what happens is that if we have several particles that are in the same cells or in the same cell of the phase space, but they have a positive and a negative sign, we can actually remove them because they do not contribute to the prediction of the behavior of the quantum system. By doing this, eventually we end up having way less particles than before. This plot here was created by not using postulate number 3. This plot that I am showing here now on the bottom right of the slide is actually the same numerical experiment, but with the application of the annihilation scheme. And what you see here is that if you apply this scheme regularly, you will eventually end up with this situation here where it is very, very clear that the number of signed particles at the end of the simulation is way smaller than the one that we had at the end of the simulation without applying annihilation. As a matter of fact here, I am reporting the number of particles for this experiment, which is the red curve, but I am also reporting the number of particles for this experiment with annihilation, which is represented by this blue curve. And as you can see, the blue curve is essentially flat if compared to the red curve, which means that essentially annihilation scheme can provide a way to speed up simulations when we are dealing with signed particles. So this is a very important point because we might have quantum systems where annihilation is not required. For example, one-dimensional and two-dimensional systems are of that nature, or at least a big majority of 2D or two-dimensional system are, while for one dimension practically we don't have to use annihilation. But if we go to three-dimensional space, then, or if we are using, or if we want to simulate a many-body quantum system, then the annihilation process is very, very important. So about the implementation of the sign particle formulation, here I am reporting a very, very simple, let's say, diagram, which shows or let's say a list of steps, to be more fair, that shows how the implementation would happen. And it's actually very simple, as you can see. The first step is going to be very, very simple. It is the beginning of the simulation, so essentially we have to set the sign particles in such a way that they represent the initial conditions of the system. Then we can go to step 2, which explains us that we have to compute the Wigner kernel, so that at step 3 we can compute the gamma function. And then step 4 becomes essentially a loop where we go from time t equals 0 to the time t equal big T, which is the final time. And what we are going to do is essentially we are going to compute the free flight of every sign particles, and then eventually, if this is the case, we are going to create new pairs of sign particles. And this is repeated, of course, for every sign particles that is in the system, and this is repeated for the time, or let's say for the period of time we are interested in. Step 9 is very interesting. This is the application of the annihilation scheme or process, and it is reported here, but as I said, this is going to depend on what system we are simulating, so this step could be actually skipped. For the interested reader here, we also have a website where this implementation has been released, and it is a free source code which is called Nano Archimedes. So if you go on nano-archimedes.com, you will actually be able to download this code, which is not a pseudocode, it's a C code that can actually work. And all the results that I'm going to show in this video were obtained through the code that you can download on this website. So we now go on a different topic, which is related to the sign particles, of course, and it is the classical limit. So what is the classical limit in this very peculiar formulation of quantum mechanics? So what happens, what this theory tells us, if h bar tends to 0? Or if, in other words, we migrate towards the classical limit. And in this particular theory here, it's very convenient to divide this situation in two different cases. So the first case is the case of free space, so we don't have any potential or forces that are being applied on the system. So this is a free system. Or we have the second situation where we do have an external potential that depends on the position and on time, and which is not 0 everywhere. So we will start from this first situation, from the first condition, which is free space. So in this particular case, if we are in the situation of free space, the potential function here is identically 0, which in turn means that the Wigner kernel, if you take postulate 2, you will see it's very easy to understand. The Wigner kernel will become 0 as well, which in turn again means that the function gamma is going to be identically 0. So in practice, since the function gamma is identically 0, we can say that we can conclude that sign particles coincide in this case with the usual Newtonian fieldless particles, and only positive signs are allowed. So we are really in the case of classical mechanics. So in the case of free space, we can reobtain classical mechanics from the sign particle formulation of quantum mechanics very, very easily. So we can now go to the second case where we do have an external potential which is not identically zero everywhere. And in this particular case, what we do is we take the Wigner kernel, the formula coming from postulate 2, and we introduce now a new variable. And if we do introduce this new variable, of course, this integral becomes slightly different. And if we continue now, we can go through a series of approximations that are very, very simple and based on the Taylor series. And then all of a sudden, you realize that your Wigner kernel can be written as this sum of integrals. If we take only the first few terms of this sum, we will have that this sum is equal to this term here, which is an integral times a constant, plus some other integral times a constant plus other terms. And it is very interesting to see if we can do anything analytically on these two integrals. And it turns out that yes, we can do things, and they are very interesting. By taking practically the first and second term, what we see is that eventually these two integrals, and in particular the first integral, will have to be evaluated between plus infinite and minus infinite. So if you take this into account and you do the calculation, you end up having this approximation here, which is described in the paper that I have mentioned before. And out of this approximation, it is possible now to compute or to calculate, the gamma function, which now looks like this limit of this sum here. So what can we say? This brings us to the point that this sum, as you can see here, will make sense only if m would be between this value here and this value here. And this is coming from the fact that now here we have a sinusoidal. And we have to take the positive part of the sinusoidal. So this can happen only if m is in this range. But for h tending to 0, this becomes 0 as well, which means that m is identically 0. In other words, even in the presence of an applied force or an applied potential, we have m equals 0, which means that there is no creation of sign particles, or in other words, creation of sign particles is forbidden in the classical limit. So again, we get to the point where we don't have creation of particles, just like it would happen in classical mechanics, and the only particles that are allowed to be simulated are particles with a positive sign. That is the summary of the classical limit that we just said. So creation of sign particles is prohibited. Particles are not fieldless anymore, so they now behave just as Newtonian particles. Negative particles are not allowed any longer, and equations of motions, as I just said, coincide with the Newton law now. So in practice, it is possible to reobtain in a very simple way classical mechanics out of this sign particle formulation of quantum mechanics. Is it possible to do anything relativistic out of this formulation? Well, the short answer is yes, but still a lot has to be done. But there is a very simple idea that has been already exploited that seems to show interesting results, and it's coming from a modification of postulate 2. Essentially, in postulate 2, we are treating these sign particles as classical particles, fieldless particles, but still classical particles. So we are following the laws of Newton's, which are known to be non-relativistic. The real equations for particles that are moving in a relativistic context would be very different, and would be these equations here, which are practically telling us that the particle now is moving on geodesics of the space. I'm not going to go through these details, but essentially you can understand that we can practically substitute this classical Newton equation with this relativistic equation now in the postulate 2 and now have a relativistic or let's say some kind of relativistic adaptation of postulate number 2. If we do that, what we can do, and this was published in the paper that I have mentioned before, what we can obtain essentially is that these fieldless particles can move on curved space-time, or in other words, they can move on geodesics. And if we do that, what we observe is that we can really see that there is the phenomenon or dilation of time, or we can also see that the induced dipole of some system is going to shift with time because of relativistic effects. Of course, all of this needs to be further investigated, but this is already an indication that we might be able to do relativistic quantum mechanics in a very different way that has been done so far. So let's see now a few benchmarks and applications so that we can validate this approach, and we will start from a very typical validation test, which is a wave function, or let's say now an ensemble of signed particles that are moving towards a barrier or a potential barrier. So imagine that this is a one-dimensional space. The x-axis here represent the position, and the y-axis here is just arbitrary units to show the density of particles that we find in space. So if we have, let's say, a potential barrier that is represented here by this red curve, so essentially it's zero everywhere, but then you have some big value here, some big energy here that prevents some electron to go through this barrier. Essentially, if you start with, let's say, a packet that is localized between 0 and 50 with a direction that goes from left to right, after some time, in this particular case 20 femtoseconds, you will see that now this Gaussian packet has changed shape and it got closer to the barrier. But as one can see, the vast majority of the signed particles are still on the left-hand side of the barrier, while some tunneling is happening around here. If we let the system go for the double of time, so for 40 femtoseconds, then the situation is very different. We now start to see the creation of peaks on the left-hand side, but there is definitely tunneling happening through the barrier. This is very, very clear from the plot. And even now we have a part of the ensemble of signed particles that has gone through the barrier and that is now found on the right-hand side of the spatial domain. We can actually describe the very same system not in terms of the configuration space, which in that particular case coincides with the spatial or with the one-dimensional space. We can also describe this system in the phase space. And this might sound as a surprise because usually in standard quantum mechanics we say that we have to give up with the concept of phase space, but this is not actually true. This depends on the formulation that you are using. So in the case, for example, of the signed particle formulation, it is possible to use signed particles to reconstruct the quasi-distribution function corresponding to these signed particles distributed in the phase space. And we can actually observe what is happening in the phase space, which is very interesting because it can provide way more details than the explanation we just provided. I will leave this to the interested reader. This explanation is provided in the paper that is mentioned at the beginning. But the main message to convey here is that if you use signed particles, all of a sudden you end up having two descriptions of your physical system. One that is the system in the space, and one that is the system in the phase space. And this is another example which is coming from the same numerical situation, but with a different starting initial condition. So in the very same way, one can use signed particle formulations to do more sophisticated things. And in this particular case here, I am showing results coming from another paper where we could show, for example, the behavior of, let's say, a packet moving in a semiconductor device made of impurities that can be phosphorus, for example, or boron, or other kinds of atoms. And what we were able to show here is that if you start from, let's say, a packet that is localized here and you let it go in time from the left to the right, what you will see is that the packet is evolving in time. As you can see here, I am showing this with the mouse, so this is the progression in time, and it continues until it gets stuck in the middle of this device, which is something that we would expect in this particular context, because here we now have an atom that behaves as an attractor for the electron, or in this particular case this is a positive ion that is attracting the electron. So signed particles can be used to simulate very, very complex situations such as the one that is presented here. Another very interesting point that I am just mentioning is that we are dealing here in the presence, we are simulating the system in the presence of open boundary conditions. This is extremely simple to implement with signed particles. This becomes extremely complicated if you try to do this with the Schrödinger formulation. So this is another advantage that one can get very, very quickly and almost for free by just using the signed particle formulation. And now this is a last example of a three-dimensional simulation. So three-dimensional simulations can be performed by using signed particles. And I am showing here practically this system where we start from one situation here where the initial conditions are represented by this packet here, and this packet is moving now from the bottom to the top of the device, and as you can see there is this progression in time that becomes very, very clear. So even three-dimensional systems, although they might sound very complex and difficult or even a daunting numerical task, this system can be approached by using signed particles even in very complicated situations where we are in the presence, for example, of open boundary conditions. So it does provide a way to study or investigate quantum systems, but it also provides advantages that would be very, very difficult to obtain by using the standard Schrödinger formulation. And this concludes this video for today. Thank you very much for your attention.